Hello students, good afternoon. We have been revising module 3, so to say, the channel capacities concepts. And yesterday I was telling about visualizing those two circles, the circle which corresponds to the source and the circle which corresponds to the destination. And when those two circles are overlapping fully, then it means that the complete information gets transferred from source to destination. And as it is an ideal case, always as channels are non-ideal, there will be a noise during communication, due to which only a part of the source information gets transferred to the destination. But even at the destination, there will be other type of information which may not be transmitted from the source at all, and that is actually related to noise itself. So in that way, this term called equivocation is defined, and this equivocation basically means that the amount of information which is captured at the destination with respect to the amount of information that was transmitted from the source. And partly, when they are matching together, that is called mutual information. Otherwise, the remaining part is called equivocation. So in that way, if we find out the equivocation, then we can find out the channel capacity. When we find out the channel capacity, we can decide upon the maximum data rate. That is the idea. Now the challenge here is, if the receiver has to know about the source entropy, that is a difficult job. Receiver need not know the source entropy as such, isn't it? Receiver need not know the transmitter entropy as such. If the receiver has to know the transmitter entropy itself, then it is again a difficult job, because at the transmitter there can be varieties of symbols being transmitted, and each and every symbol that is being transmitted, its information content must be available at the receiver also. That is a tough task or a tedious task. So the point here is, if the receiver can find out this equivocation without really knowing the probabilities of the source symbol, then based on that the channel capacity can be worked out, and based on that the maximum information rate through the channel can be arrived at. So this was what we were discussing yesterday. So in case of the symmetric channels means if symbols are going from source to destination, P of y1 slash x1, let us say, or the P of x1 itself, P of x1 and if P of x2 are same, provided there are only two symbols being transmitted, let us say 0 and 1 are transmitted. In that case, it is called as a symmetric channel. So in the case of the symmetric channels, all the rows contain the same elements but with a different order. This I had discussed yesterday also. So that is how h of y slash x equals summation of P of yj slash xi Lg of 1 over P of yj slash xi. Now there is a small derivation here. We can go through the derivation. Consider a channel matrix as follows. P of b slash a is a matrix which is containing all the conditional probabilities. Probability of obtaining b1 when a1 is transmitted, and probability of obtaining b2 when a1 is transmitted, probability of obtaining b3 when a1 is transmitted. Ideally, P of b1 slash a1 has to be 1, P of b2 slash a2 has to be 1, P of b3 slash a3 has to be 1, all other elements in this matrix have to be 0. But practically we will have some other values there. If at all I have to relate it to the matrix which is shown at the right side, ideally C1, C5 and C9 have to be having a value 1 and all others have to be having a value 0. But practically C1, C5 and C9 will not be 1, it will be slightly less than 1, and other elements in this matrix will not be 0, they will be slightly more than 0. Now in that case, if this is a symmetric channel, the C1, C2, C3, the values of C1, C2, C3 will also appear in the second row, in the C4, C5, C6, but may be distributed in a different order. Similarly, the same values will appear at the third row also as C7, C8, C9, but with a different order. Now, if you have to find out H of B slash A using the formula P of A1 into C1 Lg of 1 over C1 plus C2 Lg of 1 over C2 plus C3 Lg of 1 over C3, applying the formula. Next, the same thing with P of A2 and P of A3. This is the expression for equivocation. So, H of BA is P of A1 into S1. We can say it as C1 Lg of 1 over C1 plus C2 Lg of 1 over C2 plus C3 Lg of 1 over C3 as S1. So, P of A1 into S1 plus P of A2 into S2 plus P of A3 into S3. For a symmetric channel, S1 is equal to S2 is equal to S3. Let us equate it to S. For a symmetric channel, all the rows contain the same elements but with a different order. So now, for a symmetric channel, H of B slash A is equal to P of A1 plus P of A2 plus P of A3 into S. Now, the probability of all the symbols at the source is going to be unity in its summation. So now 1 into S is S only. So H of B slash A is nothing but this particular term given in any row, C1 into Lg of 1 over C1 plus C2 into Lg of 1 over C2 plus C3 into Lg of 1 over C3. If that is taken, that itself is going to be the equivocation. This is for a symmetric channel. Hence, for symmetric channels, H of B slash A is obtained without actually knowing the probabilities of source symbols. You can see here, even though it is defined as P of A1 into C1 Lg of 1 over C1, but C1 is nothing but P of B1 slash A1. C2 is P of B2 slash A1. C3 is P of B3 slash A1. So, for a symmetric channel, we need not know about P of A1 and A2 and A3. Without knowing the source symbol probabilities, we can find out the equivocation at the destination. That is the idea. So, this is the point with symmetric channels. But with asymmetric channels, it is not so easy. Now, in case of asymmetric channels, without knowing source symbol probability, how do we find out the equivocation? For which Muroga gave an ingenious method, and we have already worked out exercises on Muroga's method by writing those respective expressions and solving them. I will not repeat it again here because they are only exercises, and the proof for Muroga's method is beyond the scope of our syllabus itself. So we should thank Muroga for developing a method for asymmetric channels as well without having the knowledge of the source symbol probabilities. Let me revise some exercises here. Exercise number 1. In a communication system, transmitter A and receiver B having 3 symbols each have the following probabilities. It is given here. P of B1 slash A1 is 0.25. B3 slash A1 is 0.2. That means B2 slash A1 is not given, which we have to find out. Similarly, P of B1 slash A1 is given. Sorry, I think there is a mistake here. It must be B2 slash A1. While typing out, I have made this error. Take it as P of B2 slash A1, then P of B1 slash A2. P of B1 slash A3 is not given. We will have to find out. Similarly, P of B2 slash A2 and B1 slash A3 is given, B2 slash A3 is given, and P of A1 is given, A3 is given, A2 is not given. Now, as we know that the summation of each row element is equivalent to V1, we will have to find out those other values. So, directly I have written the P of B slash A here. I have written here P of B2 slash A1 is not given, but it is 0.25 plus 0.2 is 0.45, 1 minus 0.45 is 0.55. That is what is written here. Similarly, you can see here P of B2 slash A2 and P of B1 slash A2. Together it is 0.25 plus 0.75. It is 1 itself. So naturally, P of B3 slash A2 is 0. In the same manner here 0.3 plus 0.15 is given. So naturally P of B3 slash A3 is 0.55. As I have been telling you, ideally this has to be 1, this has to be 1 and this has to be 1. But practically we can see they are not that way. Now we have this noise matrix P of B slash A. That matrix itself is called channel matrix or noise matrix. Now P of A1 is given, P of A3 is given. So P of A2 is 1 minus 0.25 plus 0.35, that is 0.4. So now we can find out H of A. H of A is obtained directly by means of the source symbol probabilities, that is 1.559 bits per symbol. Now by the theorem of total probability, P of B1 I can use all that. Using the noise matrix along with the source symbol probability, I will add them now. You can see 0.25 into 0.25, 0.25 into 0.4 and 0.3 into 0.35. You can see this 0.25, 0.25, 0.3 and already we have the source symbol probabilities, that is 0.25, 0.4 and 0.35. 0.25, 0.4 and 0.35. We are using it with the noise matrix values now to obtain the probability of B1. The first column corresponds to B1, second column corresponds to B2, third column corresponds to B3. Similarly, the first row corresponds to A1, second row corresponds to A2, third row corresponds to A3. Rows correspond to the source symbol probabilities and the columns corresponds to the destination symbol probabilities. So using the theorem of total probability, we can use the first column's values along with the source symbol probabilities to obtain P of B1 as 0.2675. Similarly, using the second column, we have P of B2 as 0.49. Using the third column, we have P of B3 as 0.2425. So now we can find out H of B using the probabilities of B1, B2 and B3, which we already know now. So the destination information, H of B, information content or entropy is now 1.509 bits per symbol. Now we have the source entropy, we have the destination entropy, H of A and H of B. That is how using this noise matrix we can obtain the entropy of transmitter and receiver. That is what is asked in this particular exercise. Now let us proceed with the same exercise. Let us write the JPM for this particular previous example and we can find the probability of error now. So P of A comma B, JPM is written again using the source symbol probabilities and the noise matrix. This is the joint probability matrix written. So now P of E is 0.1 plus 0.105 plus 0.1375 using the formula for the probability of error. Respectively, when we add all that, we get 0.445. So the probability of error here is 0.445. Now the third exercise, in a communication system, transmitter X and receiver Y having three symbols each have the following probabilities. P of x1 equals 0.2, P of x2 equals 0.5, P of x3 equals 0.3. Channel matrix is given. It is 0.4, 0, 0, 0.2, 0.8, 0.4, 0.4, 0.2, 0.6 is given. Now using each column we can find out probability of B1, B2 and B3 as well, or Y1, Y2, Y3 as well. Now here is asking to find the equivocation with respect to the receiver. That means H of Y slash X by using the definition and by using the formula obtained from the diagram. Now we can use both. we can define h of y slash x mathematically, which is already shown on the screen now, or we can obtain the same h of y slash x by using the direct formula, by using that particular diagram with the two circles. Now, using the definition of equivocation, consider the case of equal number of input and output symbols, even though it is not specified here, but it is specified here, transmitter x and receiver y having 3 symbols each. So, consider the case of equal number of input and output symbols, h of y slash x is summation of I equals 1 to m of p of xi into summation of j equals 1 to m of p of yj slash xi into lg of 1 over p of yj slash xi. Now, we have everything given here. We have this conditional probability given here by means of the noise matrix, and we have this source symbol probability given here. So, all the data is available, and substituting all these data accordingly, we get this value. H of y slash x is 0.9566 bits per symbol. Now, using the formula which can be directly written. Now, using the formula h of y slash x is equal to h of y minus I of x semicolon y. That means the destination entropy minus the mutual information is going to be the equivocation. For using this formula, we have to find out the I of x semicolon y, for which we require the joint probability matrix now. So, we can write the JPM because everything else is given here. We can write the JPM. Now, JPM is P of x comma y. This is written here. Joint probability matrix is written here. All these exercises, whatever I am showing you right now, you can again refer to the notes and you can try to work out all these exercises once again, so that you will become more familiar with all these methods. Now, from the JPM, the output symbol probabilities are obtained now. P of B1, B2, B3 has to be obtained, or P of Y1, Y2, Y3 has to be obtained. It is obtained now here. Y1 is 0.08, Y2 is summation of these is 0.2, Y3 is summation of these is 0.27. So, now the entropy h of x can be obtained. H of x is already given there. Source symbol probabilities are given there, right? P of x1, x2, x3 is given there. So, h of x is obtained now, is 1.4855 bits per symbol. H of y is obtained now, because we have this P of y1, y2 and y3. So, it is 1.2659 bits per symbol. Now, using the formula or using the joint probability matrix itself, h of x comma y is obtained as 2.4422 bits per symbol. Now, the mutual information is I of x semicolon y, that is h of x plus h of y minus h of x comma y. Source entropy plus destination entropy minus the joint entropy. We obtain it as 0.3092 bits per symbol. You can see it here, h of x plus h of y minus h of x comma y. That is 0.3092 bits per symbol. Now, as we have the mutual information's content, now the required equivocation is h of y slash x is 1.2659 minus 0.3092 is 0.9567 bits per symbol. Here we have obtained 0.9566 bits per symbol. There is only 0.0001, that is the minor error there between the two computations. So, as per this formula, h of y slash x equals h of y minus I of x semicolon y. Using that, we have obtained this value. Now, these were the two exercises only for the sake of revision. With this, I am completing the module 3's revision. Let me come to module 4 now. So, in the first module, it was the fundamentals of information theory. In the second module, it was how to encode the source symbols. In the third module, it was how to characterize the channel. Now, in the fourth module, we already know the problems that are occurring during transmission because of the channel limitations. Now, channel coding theorem has already given us a roadmap, so to say, is that error coding system can exist, error correcting system can exist provided the data rate is not exceeding the channel capacity. For coming to a conclusion about the maximum data rate which can go through the channel, we had discussed in the third module about channel capacity. Now, presuming that R is always less than or equal to C, we have to develop the methods now for detecting the error and correcting the error at the destination. That is the aim of module 4 and module 5 now. In the module 4, it is block codes, and in the module 5, it is cyclic codes and convolutional codes. So, let me proceed with this revision of module 4. I think I can go from now on a little quicker because these are all already covered as such. There is no need of lot of discussion here. So, we have two definitions called block code and convolutional code. In the case of block code, the check bits are together. In the case of convolutional code, the check bits are interleaved. You will have to understand this term, interleaving. This is particular term which we use. Interleaving. Leaving means creating a gap. Inter means in between there are gaps. Means the check bits and the message bits are not actually together in the case of convolutional code. We had seen an example where check bits are only there in the final code that is being sent. The message bits are not at all present in the example which we had seen in module 5. So the point here is, in the case of the convolutional code, it is called as convolutional code because its expression matches that of convolution in the signal processing domain. Otherwise, this code has nothing to do with convolution as such. You may think that when we mention about convolutional code, you may think that we have that star operator in the code somewhere. No, it is not there. That expression matches with the expression for the convolution that is utilized in the digital signal processing domain. Otherwise, these codes have nothing to do with the actual functionality of convolution. So, in the case of block code, check bits are together. In the case of convolutional code, check bits are interleaved. Again, in the case of block code, there is a systematic block code in which the check bits are either at the beginning or at the end. And it is called as linear code when the check bits are the linear combinations of message bits. Which means, when we find out check bits, those check bits and the message bits will have some linear relationship or some well-defined algorithm. Then they are called systematic and linear block codes. Block codes can be systematic, block codes can be linear. Convolution codes are not that way, where check bits are interleaved. Now let us discuss only the block codes. We have some symbols or notations here. We use capital C for code vector, we use capital D for data vector, and we use capital G for generator matrix. Now the generator matrix is the one which is going to generate the codes that are going to be transmitted, and these codes will contain both the data bits and the check bits. I is the identity matrix and P is the parity matrix. Now this is the general expression for the code vector. C is equal to D into G in matrix multiplication. Now C is of the size N, D is of the size K. So naturally G has to be of the size K cross N. C is 1 cross N, that means totally N bits, where N is larger than K. And D is 1 cross K, K bits, where K is smaller than N. Obviously it has to be so. So now G has to be K cross N as per this algorithm. 1 cross K into K cross N is going to be 1 cross N. That is why this matrix is called generator matrix. Now how to construct the generator matrix? We have to concatenate the identity matrix with the parity matrix. I am using the term concatenation here. In general, the term concatenation is used with the strings. I am using it here instead of using the term merging or writing aside. It is better that I use the concatenation term only. So G is equal to I, we use a symbol pipe here. It is I and P are adjacent to each other. It is nothing but concatenation only. So G is now K cross N. Now if G has to be K cross N, we should have an identity matrix which is K cross K, and we should have a parity matrix which is K cross N minus K. Now we are keeping them adjacent. It is not multiplication, it is not division. We are keeping them adjacent. Only thing is we have an identity matrix K cross K and we have K cross N minus K. So naturally what happens? The number of rows is K and number of columns is K plus N minus K is going to be N. You can see here. This K plus N minus K. K plus N minus K. K gets cancelled. It is N. That is what is this N here. We know that generator matrix is K cross N. So naturally here also K cross N is there. So naturally I has to be K cross K. Initially it is K. I has to be K cross K. Identity matrix which is a square matrix. So naturally P has to be K cross N minus K. So as to have a generator matrix of K cross N. This is at the transmitter. So at the transmitter you can see that we have code vector, we have data vector, we have a generator matrix, we have an identity matrix, we have a parity matrix. Similarly now at the receiver, we have some notations now. At the receiver, we have H as Hamming matrix, S as syndrome vector, R as received vector, E as error vector, C as code vector. Now C is sent. C is sent at the transmitter. R is received at the receiver now. When R is received, from the received vector, the code vector needs to be obtained now. From the received vector, code vector needs to be obtained. For obtaining the code vector, we need an error vector. Now the error vector is obtained by obtaining the syndrome. For obtaining the syndrome, we require the Hamming matrix. Just like in transmitter, we have this parity matrix. Here in the receiver, we have Hamming matrix. You can see here G is I concatenated with P, whereas H is P transposed concatenated with I. You can see that. Now Hamming matrix H is defined as P transposed. Now P here is K cross N minus K. As P is K cross N minus K. Let me use my right hand only. As P is K cross N minus K, now this PT is N minus K cross K, P transposed. Now we have this Hamming matrix N minus K cross N. So naturally the identity matrix has to be N minus K cross N minus K. Now you can see N minus K came in the beginning, parity transposed because this N minus K came here. Because it is parity matrix transposed. N minus K cross K. Now, accordingly, we should have an identity matrix. So, K plus N minus K is now N. And this is anyhow N minus K. Finally, we have N minus K rows and how many columns here? K plus N minus K is N. N minus K cross N, that is the order of the Hamming matrix. Now syndrome is obtained by multiplying the received vector with the Hamming transposed. Now you can see H is N minus K cross N. Hamming transposed is N cross N minus K. Now the received vector is nothing but 1 cross N. 1 cross N into N cross N minus K is 1 cross N minus K. So syndrome we are going to obtain is 1 cross n minus k. So you can admire the people who used all these forms of matrices at the transmitter as well as the receiver, and all the matrices are so well defined here. So now syndrome we are going to get 1 cross n minus k. Now this syndrome is going to be verified with the Hamming transpose matrix, and the row at which the syndrome is present, that is the position of the error in the received vector. Now in the error vector, that particular position is marked with bit 1 with all error bits 0. Now the error vector is XORed with the received vector to obtain the code vector. Once we find the syndrome, the job becomes simpler. So now we can see syndrome is also equal to E multiplied with H transpose. 1 cross n minus k is the syndrome, error vector is 1 cross n, H transpose is again n cross n minus k. So that way this particular derivation was proved. Actually this particular expression was proved. S is equal to E into H transposed, that was proved. S is equal to R into H transposed is also proved. Actually these two are synonymous for that matter. But using this S is equal to R into H transposed, we get the error vector as such. Now error vector is R XOR C, or C can be obtained using the error vector now. C is equal to again R XOR E. So C is 1 cross n, R is 1 cross n, E is also 1 cross n. It is all XOR operation now. XOR operation has to be having the same dimensions here. So everywhere you can see 1 cross n. This is how we used matrix algebra for error detection and error correction. Now this is the end of my notes or summary as such. I have not put the summary of module 5 because module 5 is basically cyclic course. They are all using the polynomials. So I thought there is no need of summarizing anything. Now from next class onwards, or even from today's class itself, let me go on to discuss the problems that are left out in my notes. It is still, time is there. I still have about 15 minutes time. So let me go back right from the beginning. And I had listed some additional exercises. It may not be there in the first module. I am just quickly going through it. I am having a fast forward approach for the notes. I don't think I have any. Here I have additional exercises. In the first module, we have these additional exercises. Let me go through these exercises from now on for the next few classes. After this is over, I am going to have a regular interaction with you. Until then, this is actually one-way type of teaching as such, so to say. Because I am recording these sessions and putting in YouTube channel also, I thought even in future it will be useful to people who are wanting to learn information theory and coding. So once the discussion of additional exercises of all the 5 modules are over, then I will not be recording any of these sessions. Later on we can have complete interactive sessions only. So coming back to the first module, we have these additional exercises. Find the entropy for the Markov model shown where you can see there are 3 states here now. States are numbered as 2, 3 and 1, and all the transition probabilities are given. And using the transition probabilities, we will have to write the tree diagram, and using the tree diagram we can find out the entropy. So as the probabilities of the states are not given, see here only transition probabilities are given, state probability is not given. There are 3 states now. One way is to assume all of them as equal, but that is also not mentioned there. Let us say all 3 states are of equal probability occurrence, equally probable in their occurrence. Then we can simply say it as 1 over 3, 1 over 3, 1 over 3. But that is also not assumed here. So we can find out the state probability again by means of our expressions. Let us see. As the probabilities of the states are not given, we have to compute them by means of the state equations. The state equations are written based on the symbols being received by the particular state. There are symbols being received. For state 2, 0.2 is received, 0.3 is received. These two should be considered. Now for state 3, 0.8 is received, 0.5 is received, 0.8 is received. Now for state 1, 0.2 is received and 0.2 is received. Based on the reception of the symbols, the equations can be written now. So we can write P1 equals 0.2 P1 plus 0.2 P3. You can see here. P1 equals 0.2 P1 and 0.2 P3 because it is coming from the third state. In the same way, we can write the other 3 equations. P2 equals 0.2 P2 plus 0.3 P3. P2 equals 0.2 P2 plus 0.3 P3. Similarly, for P3, we can write 0.8 P2 plus 0.5 P3 plus 0.8 P1. Yes, P3 equals 0.8 P1 plus 0.8 P2 plus 0.5 P3. Now we can solve these 3 equations. We have 3 unknowns, P1, P2, P3, and we have 3 equations. Now solving them, we can solve it this way. Now from 1, we can write P1 equals 2 by 8 P3 from 1. From 2, we can write P2 equals 3 by 8 P3. I have converted all these decimals into fractions. Now P1 we have in terms of P3, P2 we have in terms of P3. We can use them. Now we know that P1 plus P2 plus P3 is equal to 1, right? When all the states are occurring, then the total probability is equal to 1. So that is 2 by 8 P3, substitute for P1. 2 by 8 P3, substitute for P2, 3 by 8 P3 plus P3 equals 1. You will obtain P3 is 1 over 13 by 8 or 8 by 30. Using this value of P3, obtain now P1 and P2. Now P1 will be 2 by 8 into P3. So 8 gets cancelled. P1 is 2 by 13. P2 is 3 by 8 into P3. 8 gets cancelled. It is 3 by 13. So we have P1 equals 2 by 13. P2 equals 3 by 13. You can see 3 plus 2 plus 8 is 13. We have got the state probabilities now. Now we can write the tree diagram. Entropy of each state is computed based on the symbols being emitted. Hence, H1 equals 0.2 Lg of 1 over 0.2 plus 0.8 Lg of 1 over 0.8, we get 0.722. Similarly, H2 we get 0.722. H3 we get, there are 3 symbols being emitted from the state 3. So it is 1.4855 bits per symbol. We have got the entropy of each state now. Now H is equal to P1H1 plus P2H2 plus P3H3. P1 is 2 by 13 into 0.722. Accordingly, we substitute all the values. We get the entropy of the source as 1.1919 bits per symbol. I have been telling again and again about a tree diagram. Now the tree diagram is for the purpose of obtaining the other conditional probabilities, right? So for that also we will have the exercise. For the state diagram shown, find the entropy of the source and prove that h of s is less than h of s bar. Let us see this now. This is the state diagram shown. There are now 4 states. And we have to find the entropy of the source. We have to prove this expression now. Now, we can write the state equations based on the same approach which we did earlier. For example, for P1, it is now 0.6 P1 plus 0.5 P4. For P2 is equal to 0.4 P1 plus 0.5 P4. For P3, it is 0.5 P2 plus 0.6 P3. For P4, it is 0.4 P3 plus 0.5 P2. We have 4 unknowns, we have 4 equations. And these are the state equations. Solving these equations in the same manner. Let me go quickly instead of simply repeating the same thing. Solving these 4 equations in the same manner. Finally, we get P1 equals 5 by 18, P2 equals 2 by 9, P3 equals 5 by 18. P4 we have already got here as 2 by 9. Now the state probabilities are H1, H2 and H3 and H4. There are 4. With respect to the symbols here, it is 0.971 bits per symbol here, 1 bits per symbol, 0.971 bits per symbol and 1 bits per symbol here. So H of S is P1 H1 plus P2 H2 plus P3 H3 plus P4 H4, or H of S is now 0.9838 bits per symbol. I have written as bit per symbol because it is less than 1. Now we have to write the tree diagram for obtaining H of S bar. Tree diagram for one symbol sequence is written now. From each state, let us say from P1, again the same symbol is emitted, it is 0.6 state 1. Again, if it is state 2, it is 0.4. This way, we can write the tree diagrams for one symbol sequence for all the 4 states now. Now, we know the source entropy for each state, right? Each state's entropy information content we know. So, using that, we can find out now the conditional probabilities. So, now P of 1 is 5 by 8 into 0.6 plus 2 by 9 into 0.5, that is 0.2778. P of 2 is, in the similar approach, it is 0.2222. P of 3 is again 2 by 9 into 0.5 plus 5 by 18 into 0.6, it is 0.2778. Finally, P of 4 is 0.2222. Now, H of S bar is the summation of all these things because we have common terminologies here, common values here. So, that way H of S bar is the summation. Finally, we obtain H of S bar is 1.9912 bits per symbol. So, we have proved that H is less than H of S bar with that one symbol sequence using the tree diagram. Now, with this exercise, let me stop today's class. In the next class, I will continue with these additional exercises and let us discuss all of them just for the sake of a better revision. See you in the next class. Take care and bye-bye.